Hello, this is Team Search, and we'll be giving an overview of our final design report. First, an introduction and the overview of our system. Nurses are an essential component of the American workforce, numbering in the millions and providing primary care to most patients in hospitals. Unfortunately, the number of open nursing jobs is increasing rapidly, and the profession is approaching detrimental employment shortages. On top of this, the hospital is a very busy workplace with time demands that make patient care more difficult than it already is. Disease transmission is an enduring risk. We asked whether we could improve this situation by addressing the hospital's supply chain, limiting the amount of person-to-person contact and freeing up nurses. We propose an engineering solution that will automate the transportation tasks required to run hospitals. For now, we will limit our solutions to one of the largest material needs, linen delivery. We will simplify existing systems which have not yet solved this problem adequately. Our robotic system involves a non-invasive setup with highly reliable localized navigation. Nurses and other staff won't have to worry about another distraction. Instead, our robust delivery algorithm will have what they need for their patients when they need it. And above all, our mechanically validated system is designed with the extensive feedback of nurses themselves. Our system is designed with the nurse in mind. And for an overview of our project that follows hereafter, we will first go over the definition of our problem, our preliminary assessment of the requirements, the specifications of our design, the full system design of our robot, our analyses of the design, and the outcomes of our project.
The motivating factors behind our project direction were that medical staff can be distracted from their medical duties by non-medical tasks, which will become an increased problem due to the projected shortage of nurses upcoming. Additionally, the population density of hospitals is high, which is a major factor in why hospitals are high sites of disease transmission. The major questions we wanted to ask were, can we limit the number of people involved, and therefore contact leading to disease transmission? And can this be done with an engineered system? Thinly spread medical staff and disease transmission is a problem generally applicable to hospitals, involving medical staff, patients, and the supply lines supporting occupied beds. To both limit the scope and improve the solution, we will address specific elements of the cause. Necessary to addressing the problem is knowledge of supply line analysis and modification, guidance and path algorithms for hospital use, and designs for load carrying systems. The use of solely manual labor in hospital internal supply chains is the element of the problem we aim to address. Our solution will be restricted to replacing the physical manual transportation of goods with an automated robotic system. Previous attempts have been made to integrate robotic automation into the supply chain of hospitals, but since these are not yet widespread, we believe there is need for improvement. By simplifying the navigation system and individualizing the transportation role of the robot, we hope to improve upon these current systems through simplicity. At this point, we have established the general problem we are trying to address. With benefiting nurses in mind, our goal became alleviating daily time-consuming tasks. We found it interesting that some of the most trivial tasks took the longest. For example, waste collection and transportation of clothes/linens were the two most time-consuming tasks. If we built a robot capable of transporting either or both of these, we could save more hours per week than any of our other solution spaces. And we eventually settled on linens. In our case, these robots have the potential to free up nurses and other staff to have more time for patients and other important tasks, while also helping to reduce unsanitary interaction. We felt it was important to get some opinions and thoughts from nurses, and as they are our primary audience. To do so, we researched currently existing feelings towards robots in the healthcare industry and talked to a few nurses currently working in the field about their thoughts on the idea of robotic transportation helpers. Many felt robots were helpful, saved time and energy, were fun to work with, and were completing thankless jobs that people felt were better to be done by a robot simply because of that. We then talked to a few nurses from the University of Johns Hopkins and UCLA. They both agreed that the cost of transporting material and waste was an overhead cost, so having technology to handle that efficiently could be of benefit for nurses, as more money could be put towards other areas and nurses in general would have more time for patient care. They both noted that the fatigue of doing some of these tasks was a real problem, and they both talked about just how much walking per day is done manually by nurses in transportation of various things. On the other hand, both did question reliability and consistency of robots for these tasks, in addition to a lot of questions on the integration of these robotic systems. The aim of the objective tree method is to clarify design objectives and sub-objectives and the relationships between them. The broadest objective for the artifact was to create a reliable, easy-to-use robot. From this main objective, sub-objectives would be reliability, ease of use, and good operating characteristics. The rest of the objectives could be categorized as sub-objectives of one of these three. the lower objectives, such as object detection, being the means to achieving the higher objectives they are connected to, reliable operation. The block diagram consists of 3 blocks that are power, controller, and chassis. The power subsystem is responsible for power delivery from the battery to the other subsystems, as well as recharging the battery. The input of the power subsystem is electricity from the external power source, and the outputs are stored in the battery and heat generated due to inductance. The controller subsystem takes the data from the user or sensors and then calculates its next move by using various algorithms. The inputs of the controller subsystem are signal commands from the end and raw image data from the sensors. The outputs are various instructions that control the current of the actuators. The chassis is where all the basic components of the mechanism work together. The inputs of this subsystem are current that actuates the motors and external forces that are applied to the chassis. The outputs are both wheel speeds, heat from the electronics and friction, and the displacement of the object. The goal of the performance specification method is to give an accurate specification of the performance required of a design solution. At this early phase of the design process, more general specifications were used to leave a sizable range of options for the final design. The performance attributes considered are those most necessary to the basic function of the robot and its environment. An example would be that it does not need to be able to work at extremely high temperatures or low temperatures, since the environment of the hospital that the robot will be traveling through does not involve these temperatures. For values such as battery life and payload, a reasonable minimum value to satisfy basic requirements was chosen at this stage as an aid for the future. The dimensions of the robot were chosen so as to not be too invasive in the hospital environment, and a lighter robot can carry a heavier load for the same actuator output. The goal of the quality function deployment method is to set targets to be achieved for the engineering characteristics of a product. Points allocation determine the percentage weights to each attribute. The most important attributes were reliability, simplicity, user-friendliness, safety, and a long battery life. We evaluated what we viewed as competing products based on function against the set of important attributes created. The 4 products chosen were the Tug Drawer and Tug Exchange made by Atheon, and the Evo Cart 3 and Evo Cart 5 made by Oppint. Then we took the attributes and created a set of engineering characteristics that are the means to the attributes to measure each competitor against. For example, longer battery life is most directly related to power consumption, weight, and payload, as well as being related to material, downtime, acceleration, and working temperature. We use symbols to represent the strength of the relationship between each attribute and the engineering characteristics responsible for them. The correlation between different engineering characteristics is represented by symbols in the roof matrix to demonstrate the relationships that exist between some of them. One example is that power consumption is directly related to weight and payload of the robot. Using the competitor values, we came up with a set of target figures for our design to score on the chart, as seen on the right side. Then we moved on to rational methods, where we took a more formally oriented approach. One way to accomplish this was with the morphological chart. The columns represent solution ideas, and the rows represent sub-functions we need our robot to accomplish. The first sub-function we considered was how to hold the object. We included many possibilities in this chart, ranging from a security base like a safe to more open solutions like trays. In the end, we went with trays, since linens are not sensitive materials that need to be kept inside of a safe or in drawers. We then needed to consider the impact of these robots on space inside the hospital, so we considered different transportation methods. The best solution we found and got approved was placing lines on the floor of the hospital up against the wall, confining it to the guideline-based hallway space set aside for objects. Next was accessibility, the fundamental question of how and who our robots were going to interact with. This impacts interface, display, and a lot of other aspects. So this was an important area to discuss different solutions. Would we want the robot to only interact with patients, nurses, or both, or require no human interaction at all? This raised the question of our targeted audience. Who are we trying to help most? Which was nurses. So we went with a nurse-only interaction interface. It also affects our sanitation. If we interact with patients, we definitely increase our chance of spreading disease. The last couple of functions are mechanical and algorithmic design choices for the robot. How the robot's going to move with the ground interface, and how we're going to implement the line following algorithm using IR sensors in this case, and LiDAR sensors to detect obstacles. Overall, this was a useful way to explore how exactly we could best design our robot to best solve our problem. This will be discussed extensively in section 4, but we will introduce our main competitor here, as we used in the initial research to formulate our system design objectives for the subsequent weighted objective chart. Our main competitor is Tug, an autonomous mobile robot also specifically made for hospitals by Atheon, a robotic company launched as a way for healthcare administrators to cut costs, save on nurse turnover, and limit injury risk. Here's a quantifiable specifications comparison to gain an idea of the systems. With this established, we used a weighted objective chart to quantitatively compare our subfunction solutions to our main competitors to prove our marketability. After considering all the subfunctions from our previous chart, we scored our two main ideas. The main objectives are then listed on the left, including navigation, reliability, cost, safety, speed, and aesthetics. Then all the objectives were assigned a weight out of 5 based on the importance of the robot accomplishing its tasks. We felt reliability, cost, and safety were the most important objectives to accomplish with the highest success rate possible that is also safe for medical personnel and patients. Otherwise, failing to solve the problem at a fundamental level would occur. For the two candidates, each objective was given a score out of 5, and a subsequent utility score, which combines the score and objective weight, was given out as well. From this analysis, we could see that our robot scores higher in this than the tug robot.
So I'll be talking about design specifications, and our first specification is adaptability. And so this was one of our most important design requirements per kind of consumer feedback and our analysis of like what could set us apart. And so what we mean by this is generally we're going to be measuring by size or hospital size. So generally it's based on geographic region and classification. So classifications include stuff like rural, urban non-teaching, and urban teaching. And so a rural hospital with 25 beds and 300 staff members is going to have a lot different needs than a state-of-the-art urban hospital with like 500 plus beds and 3,500 staff members. And so our main competitors integration involves like an internal mapping process and central system management and user interfaces. And this just really isn't necessary for isolated hospitals where like the average intake of patients is only about 7. And so we wanted to have a system that was more non-invasive setup, largely simplified investment, and can be tailored to like any different size of these hospitals. And so our goal is to be like as self-sufficient as possible to kind of ensure nurses are indeed getting more time with patients. And so our next design specification was reliability. And so in order to create a minimal and simplistic solution for nurses, as kind of required by our adaptability, we needed to create a system with highly proven accuracy. And so we began with mechanical elements, and so to ensure our system integrity. And so this included like structural loading, suspension, cooling, tolerance checks, tipping checks, and a whole lot of analysis that will be discussed later. And then at the same time, we were with that established, we were able to focus on our navigation algorithms. And so through our controller evaluation, trajectory analysis, and simulation, we were able to ensure that our robot is highly reliable. So now next is safety. So this was another main design component. And with this in mind, we followed the International Organization for Standardization's requirements for robotics and system integration, in addition to like CDC and hospital building guidelines. And so we were able to adhere to the following that was specified as per them: cableless teach pendants. And so this was to prevent unintended operation of another robot that may result in a hazard to personnel. And so that one was pretty easy. Human robot collaboration. So like if operator is to interact with the robot, they need certain safety controls and safe state positioning to limit like its motion and fully stop to ensure safety. And then also we needed emergency guard systems, and then database diagnostics. So just data to help improve system initiatives and look at the robot's faults and failures. And so we addressed all of these, and we will talk about that later in the presentation. And so then in terms of cost, as talked about, was sort of our emphasis on easy adaptable system integration. There's another portion which is clearly cost. And so a small rural hospital is going to have a lot less of a budget for this sort of thing than UCLA is. And so this is also heavily reliant on our competitor. And so we feel this was a main area that we could set ourselves apart once again. And so obviously efficiency and costs are a top priority for hospitals. They are still a business. And so by reallocating nurse time, we're improving productivity, limiting injury risk, and also our goal is obviously to increase worker satisfaction. And so our goal is to obviously enhance the nurse workforce as opposed to replace jobs. And so we feel that this way we can offer kind of improved service all around. And lastly, there's aesthetics. And so we felt that it was important for like a newer technology in a very vulnerable environment to have, in addition to having functionality, it needs to be welcoming. And so, its physical appearance can just instantly affect how people perceive it. And so therefore we felt it was kind of high importance that the robot be designed in such a way that its skills and functions are like quickly and easily communicated and not ambiguous. And so through a couple iterations and user feedback, we feel we've worked to achieve a sellable and original aesthetics.
Here's an overview of our system. The frame is made out of 6061 alloy aluminum square tubings as opposed to the originally proposed PP copolymer. The corners are reinforced with gussets and the rest of the junctions will be welded in place, since the robot is unlikely to experience any lateral load. 6061 alloy aluminum is much stronger than most polymers, and its tensile strength is 4 times higher than copolymer. Now, the frame is much easier and more cost-effective to construct with stock tubings compared to polymer. Even though the cost of raw materials for aluminum is higher than plastic, the quantity needed is much less. The need for creating mold for plastic forming can impose another $3,000 into the cost. Precision parts such as bearings can be fitted into machine billet blocks rather than held in place inside polymers that will deform over time. By connecting the wheel shaft directly to the motor shaft, we will reduce the powertrain loss due to heat and minimize part wear. The wheel shaft and motor shaft are held in place coaxially with a coupler. The keys ensure that the torque will be transferred directly from the motor shaft to the wheels. The set screws are not designed to prevent shaft walk during rotation, so we put C-clips on both sides of the wheel bearings. The actuator operates on 24 volt because 24 volt is a very common voltage to use among our competitors, in that it is safe and can provide enough electrical power compared to lower voltage rated motors. It can provide sufficient torque to break initial rotational resistance and has maximum RPM that will enable our robot to reach its top speed. That way, we do not need to design a separate gear reduction mechanism to trade torque for speed or vice versa, thus reducing the complexity of the drivetrain and minimize part wear. The inner shell is made out of 18-gauge aluminum sheet metal. It is the host for all electrical components, including motors, sensors, batteries, controllers, drivers, and the power supply. These components are subject to cooling by convection from 4 60mm fans on the sides. The fan grills are wire shapes because studies show that they can provide the highest mass flow rate. The cover has perforated holes for the fans to draw air from the top. This design helps filter out the dust while eliminating the chance of letting water into the system. The holes are directly on top of the batteries and motors, so they are the first to be cooled by incoming air. Underneath the cover, there is an air filter that will block dust up to 40 microns.
For the chassis to storage frame suspension, we have 4 brackets bolted to the storage frame and resting on 8 springs. They move vertically over pins mounted in bearings attached to the chassis frame. The suspension has a resonant frequency higher than the expected disturbance frequency band. Next, we designed a frame of hollow aluminum 6061 alloy beams with mountings for insertable trays. Even with a very high factor of safety, the storage assembly adds only 17 kilograms to the robot's mass. We wanted to give the robot a more appealing appearance, so we modified the plastic housing with more aesthetics in mind. The front of the shelving unit is now open and easy to access, minimizing surface contact and easing use.
Alright, this is the electrical and computer engineering part of our design. We break up our controller subsystem into the physical controller itself, which is an Arduino Uno, the controller algorithm, and the IR sensors, and finally the LiDAR sensors. So just starting off with a look at the IR sensors, We decide to use infrared LED to emit IR light toward the ground, and that's reflected back onto a photodiode if the light is transmitted onto a bright surface. So we decided our line would be white, which is a bright color that will reflect IR light. And we're going to have photodiodes and infrared LEDs on each side of the line, with black surrounding the sides of the white line. So that means, for example, when the left side's LED shines light onto the line, because the robot's moving off course, then the left side's photodiode will pick up IR light reflected off the line, and in response will slow down the left wheel of the robot. So the robot stops veering towards the right and goes back on course. Moving on to the LiDAR part of our design. We used a Garmin LiDAR Light V3 sensor, which has a measurement range of 40 meters. And below is the circuit diagram that was provided in the datasheet that details how to integrate an Arduino Uno with the LiDAR sensor. Essentially, pulling the mode control pin low triggers a single measurement, and the device will respond by driving the line high with a pulse width proportional to the measured distance at 10 microseconds per centimeter. And if the mode control pin is held low, then that means it's going to continuously measure indefinitely, producing a variable frequency output that's proportional to the distance. So essentially, the frequency of the output is going to change depending on how close an object is to the LiDAR, how big that distance measurement is. So using this information, we can convert the frequency into a distance measurement for a controller, and then we can use that information to tell the motors to stop or move a certain way, depending on where objects are and how close they are. Moving on to robot movement, we decided to use two-wheel differential drive as opposed to independent steering because it's a lot simpler, and also power performance converges for larger radius turns. And we decided to use front-wheel drive because the ball transfers we used are point contacts to the ground, and so they don't contribute to the direction. So here you can see we derived the equations of motion for a robot based on how we have the drivetrain set up. And over here we have a block diagram of our obstacle detection sensor formulation. So we first note that our robot moves at up to 3 miles per hour. And we're going to incorporate readings from our LiDAR sensor into our microcontroller code, as mentioned before. And we're going to stop specifically at 1.5 meters before hitting an obstacle if our robot's LiDAR sensor detects an object. Moving on, we also created a state chart. So we have a set of different states depending on the robot's environment, and we have a response that corresponds to each state. So here the factors are if the robot is in a slow zone, if there's an obstacle in front, or there's an obstacle behind, and we take all possible combinations of these situations. And below you can see the actions taken by the robot depending on which state it's put in. For a controller, we also used a path-following PID algorithm, similar to our analytical Python simulation, but this time we don't base our error on angular velocity alone. This worked well for reaching targets at defined points on a grid where less direct paths were used. But our Weebot's navigation is more realistically set to follow against a wall, and thus a more linear approach makes sense with a heavy emphasis on handling 90-degree turns. Here's a general system diagram to describe the overall layout of the controller, along with the function definitions. Moving on to our controller algorithm, just a closer look at our PID algorithm that was mentioned before. For the PID tuning process, we followed an approach based on our sensor setup. We had 2 arrays of 8 sensors on the front and the back of the robot, and we considered them separately here. The general process was that we'd start with the coefficient Kp, which is proportional control, given Kd and Ki equal to 0. So derivative and integral control coefficients equal to 0. So first we determine the initial KP. Each sensor returns a value between 0 and 1,000. For an array of 8 sensors, this means total we would return a max value of 1,000 times the number of sensors minus 1. So our range is between 0 and 7,000 units. And our goal is to follow exactly in the center, which corresponds to the maximum value divided by 2, which is 7,000 divided by 2, which is 3,500. So therefore, our goal is to be around a value of 3,500 for each of the sensor arrays at all times. And if we consider the worst case scenario when we drift off the line to the left or the rightmost sensor, so we're not exactly in the center anymore, then the proportional control coefficient multiplied by the error will reach 100%. Using this worst case, we can determine that our proportional control coefficient should be equal to 0.025. We then chose the integral control coefficient without the derivative control coefficient yet. We set the KD equal to 0. We simply increased the integral control coefficient until the system oscillated quickly enough. Lastly, we moved on to choosing the derivative control coefficient. So we increased that coefficient until the system minimized oscillation, and that ended up being 3 times the proportional control coefficient, which is 0.075. So that's the PID algorithm. In terms of worlds, for Weebot worlds, we wanted to take advantage of Weebot's more realistic displays in addition to functional testing. So we created multiple worlds with different line path tracks. And these different tracks encompass different aspects of our navigation. So over here in our figures, you can see that there are straight lines, transitions from straight lines to edges, which represent slow zones, and also vice versa. You can see that there are walls, which you can move around to test out the obstacle detection. We also defined what would happen for junctions for a robot. So what we did was we decided that if nurses wanted to stop our robot in front of the room they're at, then all they would have to do is lay down a line path, a line strip perpendicular to a straight line path. And this is recognized as a junction in our controller code, and our robot will stop at a junction. Junctions are also important for our battery life. Weebots doesn't really allow us to simulate battery life, so we decided when our robot moves around and detects 20 junctions, it'll stop. Moving on to the drivetrain subsystem. This subsystem is broken up into the motors used to drive the robot and the battery used to power the motors. So as you can see here, this is how the battery and the driver and the motors will be connected. The driver outlines in its data sheet which pins should be assigned to which components in the circuit. The high-level overview of how this will work is that our Arduino controller will control the motor driver by sending analog voltage signals to terminals S1 and S2 on our motor driver, using these terminals to control the speed and direction of the motors.
We have conducted a series of analyses on the robot in terms of both mechanical and electrical design. Here is a static analysis of the frame with loads in various locations with a total static loading of 3,200 newtons and 100 newton meters of bending moment at the base of the motors. The maximum deflection is under 0.75 millimeters. We also did a kinematic analysis on the robot. Through the Weebot simulation, we have great success in accelerating the robot to its top speed under just 1.1 seconds without slip. The theoretical maximum torque needed is 1.7 newton meters, which is easily achievable by our actuator. Next, we also conducted a static analysis on the shaft, where the spokes are fixed on one end and a 10 newton meters torque is evenly applied on the other end. The result shows there is no permanent deformation or any risk of premature failure due to the torque exerted on the shaft. Here we set up a flow simulation on a simplified model of the robot. The ambient temperature is set to be 20 degrees Celsius and the fans are set to operate at 1800 RPM. We use the heat generation rate from the datasheets provided by manufacturers for conducting the simulation. The result shows the temperature spectrum of internal flow is around 50 degrees C, which is well within the temperature range for safe operation. Here's a particle tracing simulation we did in SolidWorks for dust particles of 50 microns in size. According to the Excel data, 30 out of 50 dust particle samples will eventually reside in the robot. However, the air filter we choose is capable of filtering particles that are less than 40 microns. Therefore, we conclude that the robot will not have much dust inside once the air filter is in place.
To validate our design of the storage system, we performed static finite element analysis of the shelving frame and found a very high factor of safety even under excessive loads up to 80 pound forces. Then to validate our assumptions about the suspension springs, we expected the suspension mounted frame to act as a second order spring mass system. We validated this with SolidWorks, which gave us excellent fitting of the experimental data to theoretical data. We then chose a set of 8 suspension springs that keep our resonant mode significantly above the 5 Hertz where we expect the disturbances to be. Another issue that we came up with in our discussions was the potential tipping of the robot. We determined this would be caused either by external contact or drive kinetics. For external contact, it requires an average of 14.6 pound forces applied to the top of the robot to tip it fully, a force that no normal operator should be applying to the robot in a reasonable situation. In emergency collisions of objects or people with the robot, the question of whether the robot falls over or stays upright as an obstacle either way, we believe is an irrelevant question. For the drive kinetics, it turns out our drive does not actually deliver enough torque to even lift the rear wheels from the ground, so we should not be tipping due to driving around in the hospital.
When contacted from the side, the robot's proximity to the wall keeps it from tipping over into the hallway for realistic contacts. The robot being 5 centimeters from the wall also means that someone would have to intentionally knock it over from the wall side in order to tip it into the hallway. Contacts directly from behind require the least force to tip over the robot. However, this would require someone to run into it or push something into it from behind, meaning they intentionally put it in their path. In the event of an emergency, a stretcher or person running into the back of the robot will have already impeded their own path, regardless of whether the robot being tipped affected them or not. Additionally, when contacted from behind in this way, the robot falls within the bounds of its allotted space in the side of the hallway. In a worst-case scenario, the robot is hit in the outside corner. This results in the robot leaving the 60 centimeter space allotted to stationary objects and entering the additional 30 centimeters allowed for wheeled objects, where it can be pushed back against the wall. The line-following algorithm prevents the robot from moving any further in this configuration where it is skewed into the hull.
We also wanted to account for the possibility of 2 robots encountering each other on the same path in opposite directions. Using overestimated values from the Bispebjerg Hospital, which is a 500-bed hospital in Denmark, we found that we likely will be able to address the daily linen distribution needs of each hospital floor with a single robot. This eliminated or at least significantly reduced the need to account for the possibility of assigning more than 1 robot per floor.
So this is the electrical and computer engineering part of our controller evaluation. So in our initial research, we looked at possible controller options to best fit our design capabilities, and we evaluated the performance of each option. We first chose a wide variety of control methods, ranging from database to more traditional, in order to compare benefits and downfalls of each. To numerically assess, we took a look at previously conducted research on line following simulations, where robots were scored based on following a track from a starting point and ending when one of the following conditions happens. 1, the robot completes the path and reaches the endpoint. 2, the robot loses the track. Or 3, the robot turns and follows the track in the opposite direction. Essentially, P-controlled algorithms had a higher score than various forms of Q learning. We then looked into other controller algorithms and line detection sensor subsystems, like quadratic and linear interpolation and using weighted averages. The figure below shows the experimental verifications of the line detection algorithms through weighted average on the left and quadratic interpolation on the right by using calibrated sensory outputs as done in a study at the Longhua University of Science and Technology. Looking at the next table, we can see that the robot trajectory is the path of robot movement from one point to another by following a predetermined path, as discussed earlier. And in other words, the trajectory is the result of the robot's action based on the path pursuit controller. And as we can see, the trajectory follows the shape of the track line quite closely. So the tracks here include a U shape surrounded parallel corridor and embedded. And we felt this was a holistic and deterministic way to try and generalize our systems testing. So based on the figures here, our robot's able to move according to the line paths. The trajectories are perfectly centered. So we can see the error deviation data in this figure. For each of the tracks seen above, ran across 500 trials, and our deviation percentages were extremely low.
All right, so here's kind of a video of our Wiimote simulation. We just wanted to show a couple of kind of live time things just to make it clear and demonstrate some of our capabilities. And so here's just a brief overview. Sorry for moving it around so much, but so first thing to notice is you can see in the bottom left corner, and sorry again, it's kind of cut off, but you can see the type of path we're following, and then in the parentheses are the speed of each wheel. And so here we're edge following, and it says that there, and then it kind of corrects speed in a couple of cases, and it's a little jumpy just because I kind of sped the video up because it goes pretty slow in real life, but that's just to kind of ensure the safety of the turn and everything. So yeah, the first thing to notice in this video is sort of the line to edge following. There are no tipping and just straightforward there. And of course, we're reflecting it down there in the console, so you sort of get like a status update. Slowly chugging along here. And so here, coming up to a junction. And so it's going to freeze in a second here. And this wouldn't happen in real life, but you can see in the bottom left there, it just prints junction one time. And so that counts the junction, and then it just keeps going. So smooth junction handling there. Next, obstacle in front. And so move it in during the simulation, it stops. Again, it says obstacle in front, stopping in the bottom left. And then moving it back out, it keeps going. And then moving it back in again, like halfway, it also stops too. And then here is an obstacle in front of a slow zone. And so that causes the robot to move backward because we're assuming like a slow zone would be a door or something. And if there's an obstacle in front of the slow zone, we can't be in that zone. And so it backs out of it or it keeps going. And then you saw it kept moving forward after the obstacle was removed. And so now I'll be talking about design outcomes versus our requirements and sort of our end comparison. And so in order to review our system, we validated our design outcome through a couple different methods and analysis. And so one of these was through nurse review. And so we conducted 3 separate nurse reviews, one in week 3, one in week 8, and one in week 10. And so quickly to summarize, in week 3, we had the nurse, we asked a lot of questions in week 3 and sort of talked about like where our system would be best placed and in certain emergencies, like what can we do? And so we sort of handled a lot of these scenarios that we weren't really sure of without a true medical opinion. And so the first nurse request we got from that main week was that the robot needs to be manually pushable in case of emergency. And so correspondingly, we designed an on-off switch. We significantly lowered our base weight compared to competitors. And so we came in at only about less than 75 pounds compared to like 220 from our competitor. And then we took this in consideration for our free wheels design. And so we have 2 drive wheels in the front and then 2 free wheels in the back so that it can be easily pushed when the motor is turned off in case of emergency. Then in week 8, so we had a couple requests and information we got from the nurses. And so one was we had a lot of feedback that people were worried about the floor and how dirty it would get and if that would affect our line and the IR sensors accuracy. And so our nurses told us that floor cleaning is a category 2 according to the CDC, which means clean about once a day. And they have a list of like 5 EPA registered chemicals that they use. And so in order to combat this, we picked a chemical resistant clear top coat to cover the line to avoid sort of walking damage and cleaning damage. He also told us that we need to clean the robot. And so we're advising cleaning once per day with approved COVID-19 surface wipes It's what they use at like UCLA and all sorts of hospitals. And so pretty standard and probably just during charging or something. And then hospital floors are typically covered in welded sheet rubber. And so nurses also often use like surgical tape for marking certain locations within rooms. And so that's the same tape we decided to use for our line. It's double-sided dry fit adhesive, and it's got approved strength and durability for hospitals. And so that then covered by our chemical resistant layers, kind of how we're setting up the floor. Battery, the nurses need to spend the less time nurses need to tend to the robot, the better. And so we formulated an automatic navigation to a charging station based on a loop counter, and that was kind of explained in section 5. Then in week 10, we met with Dignity Health, and so they're a Californian hospital organization, and this was in order to sort of get like a business perspective on our product. And so we just kind of got general advice. He told us to take advantage of COVID in terms of marketing. So we kind of include that in our engineering pitch and sales pitch. He told us to make sure it's generalizable, which was one of our main design criteria, is adaptability. And so that was good. And then most importantly, he told us to cover speed, investment return, aesthetics, and self-sufficiency. And so we have a faster max speed than our competitor. We have a pretty large decrease in price. Aesthetically, we were approved by healthcare and business workers, and then we have our increased reliability and predictability. So then to look at our design requirements from a different perspective, we used a quantitative competitor review. And so we quantitatively compared TUG to ourselves, and TUG's kind of our established competitor, as we've mentioned a few times. And so first is adaptability. And so required mapping, TUG requires a mapping with emptied out hospital as opposed to our simple line installation. And so we feel that we are much more adaptable. And since it's kind of manually installed, it's a lot easier to sort of go through the process of like where you would want the robot to go and certain things like that. Whereas mapping with a hospital is costly. Next, in terms of reliability, TUG is 17 years established. And so that obviously gives it a little bit of an edge. But we've done everything we can previously kind of mentioned in sections 5 and 6 to sort of establish ourselves. And so from suspension analysis, cooling checks, tolerance checks, tipping analysis, simulations, and track deviations, we feel we've increased our navigation predictability. Because of the reliability, we know accurately where the robots should be at any time. And we feel like we've obviously increased our navigation reliability, given that we have such a low percentage of error in track deviation. And so next was safety. TUG has a couple of different carts that they use, and some are more secure, and they have like audible features. That's one thing we don't have. And so where we make up for that is in terms of like structural safety. We also included analysis across 500 trials for each of the tracks we built. And we had max speed sort of confirmed by the CDC regulation and techniques for like regional safety. And so we also designed a switch for manual emergency control and the emergency obstacle detection subsystem. And then cost, we're only 17% of the cost. And so that's including line installation and a 4 times markup, which is common in like medical fields. And so we're really happy with that. And then lastly, aesthetics, sort of simple colors, for that non-threatening look that we talked about, minimal external lighting, and sort of a modern, unique design that we feel competes well with TUG. And so quantitatively, our robot kind of performs at an equal or better level across almost all of our design requirements. And so we're really happy with this, and we think it's a great way to sort of assess what we've achieved.
In conclusion, we've demonstrated the ability of our robot to adapt to hospital environments with its robust mechanical and algorithmic design. It safely operates inside hospital regulations and with mechanical integrity. With even minor modifications, our delivery scope can be expanded to medicines, foods, and other materials in the hospital. And overall, We've provided a powerful solution to staff overworking and a new method to help prevent diseases in hospitals.